Time. It's the one dimension we all move through together, in one direction, at the same speed. But in the context of the universe, time becomes far more than a ticking clock. It's a force that shapes the cosmos, sets the rhythm of galaxies, and determines the ultimate fate of everything. The concept of time's arrow, the one-way flow of time, is intimately tied to the expansion of the universe. Ever since the Big Bang, space itself has been stretching, dragging time along with it. The farther we look into the cosmos, the further back in time we see. Distant galaxies are time capsules, their light revealing a younger universe, full of hot stars and turbulent forces. But why does time move forward? According to physics, most fundamental laws are time-symmetric. They don't prefer a direction. What gives time its irreversible quality is entropy, the gradual increase of disorder in a system. The universe began in an incredibly low entropy, high-order state. As it evolves, entropy increases. Stars burn out, galaxies disperse, and order breaks down. This growing disorder defines time's flow. This progression has led to a cosmos in motion, but that motion isn't endless. Scientists now know that the universe's expansion is accelerating, driven by the elusive force of dark energy. As galaxies drift farther apart, space itself grows faster than gravity can keep it together. Over cosmic time, galaxies will recede beyond each other's light, vanishing from view. This leads us to one of the most fascinating questions in cosmology. What will become of the universe in the end? There are several competing theories. The most widely accepted scenario is the heat death, or the Big Freeze. In this model, the universe continues to expand forever. Stars eventually burn out, galaxies fade, and black holes evaporate through a process known as Hawking radiation. Over unimaginable timescales, trillions of years, the cosmos becomes cold, dark, and lifeless. Entropy reaches its maximum, and time itself may cease to have meaning. Another possibility is the Big Rip. If dark energy strengthens over time, its repulsive force could eventually overcome all other forces, tearing galaxies, stars, planets, and even atoms apart. The very fabric of space-time would be shredded in a final catastrophic end. It's a dramatic vision of destruction, but one still being debated in theoretical physics. There's also the possibility of a big bounce, a cyclical universe that expands, contracts, and re-expands endlessly. In this model, our universe could be just the latest iteration in an eternal loop of birth and rebirth. Time would still have an arrow, but its scope would be infinite, looping endlessly in cycles too vast for us to grasp. Then there is a theory that rewrites everything: the simulation hypothesis. What if time is not a fundamental property of the universe at all, but an emergent phenomenon, a byproduct of how we process information? In such a scenario, time may be an illusion, and the universe itself could be a kind of hyper-advanced computation. While still speculative, this idea forces us to rethink not just time, but reality itself. No matter the model, what becomes clear is that the universe is not static. It's in transition. Galaxies are not fixed in the sky. They are fleeting features in an ever-changing tapestry. Stars are born, live, and die. Black holes form and vanish. Even space itself, once thought to be a passive backdrop, is an active player in the universe's story. And through all of this, we find ourselves in a rare and precious moment. A time when stars still shine, galaxies are still visible, and life can exist. We live in the stellar epoch, a brief window in the universe's timeline where complexity is still possible. Future civilizations, if they exist, will face a different cosmos. In 1 trillion years, all but the closest galaxies will have disappeared from sight. Without the cosmic microwave background to study, without other galaxies to observe, Those distant scientists may never know the true nature of the universe's expansion. For them, the universe may appear small, static, and eternal, a cosmic illusion caused by a lack of evidence. But we live in a privileged era, one where we can still read the universe's past in starlight and map its future in equations. An era where we can ask, where is all this going? And just as entropy increases in physics, so too does knowledge in science. Every discovery adds to our understanding of time's trajectory. Every theory brings us closer to glimpsing the ultimate fate of all things. Still, the most profound truth may be this: even if the universe fades into darkness or resets in endless loops, our curiosity leaves a mark. The act of asking why is a kind of rebellion against entropy. It asserts that while everything may decay, meaning, however fleeting, can exist in the in-between. We may be brief flashes in the grand timeline of existence, but in asking these questions, we light up the dark.